Okay. Cool. I think we're recording. All right. So this session is going to be building off of what Kevway has already shown you guys with Xarray. He's essentially showed you all the core features of Xarray that we will be employing here in this session, just with real data. And we're going to be calculating ENSO with Xarray. Let me just do that so it's easier for you guys to see. So hopefully we will cover all of these aims. So we're going to first load in the sea surface temperature data from a model called CESM2. And we're going to use the where method or function that Kevway, it was one of the last things Kevway showed you on masking the data. And then from that, we're going to compute the climatologies and anomalies using this group by function method. And then we're going to smooth the data by using this rolling method to compute a moving average. And then finally, we're going to compute, normalize, and plot the Nino 3.4 index. So first, as always, we have to import packages. So please do this on your own, in your own notebook alongside me so that we can all practice and hopefully this becomes, sears into muscle memory. So we're first going to import the Cartopy package, the plotting package, and we're going to rename it as CCRS. We're going to import matplotlib, it's PLT, import Xarray, of course, as XR, and we're going to use data that the Pythia people have already cleaned up for us so that we can do this exercise. So we're going from Pythia datasets, from their own repo of datasets, we're going to import datasets, all caps. Okay, let's run that. And while that's running, I think Daniel already talked to you a bit about what Nino 3.4 index is, but basically it shows, it's supposed to measure, it's an index that it shows the temperature anomalies, sea surface temperature anomalies over the Pacific Basin, specifically in this boxed region here. And an El Nino event is associated with, I always get this mixed up. An El Nino event is associated with anomalously warm events, and then a La Nina is usually associated with anomalous sea surface temperatures that are colder than usual. Here you could read this in your own time, and I also included a link somewhere where you can click to the NOAA website and that's weird. For some reason things did not save properly, so I can include the NOAA link later and update this file. So this exercise, we're trying to recreate this plot. This is our goal here. So see El Nino, that it's highlighted red. The red peaks represent El Nino events. And then the blue peaks represent La Nina events. And so we're trying to replicate this figure where it shows a time series from 1950 to 2020, illustrating when El Nino and La Nina events occurred. Okay, so first we have to bring in the data sets that Pythia has so kindly provided for us. So first we will fetch the first file path. So we're going to call this file path equals datasets, all caps, data sets, excuse me. And then the file path is called CESM2, the model name, SST, the variable, data, .nc, the file. And then we want to open this first file. So let's call it data equals XR open data set. If you hear noise in the background, that is my cat trying to get into food. So he's always hungry. anyways, so we're going to open a second file file that has the area, I believe. So just call it file path 2 datasets dot fetch CESM 2 grid variables dot NC. And same thing, we're going to open it. So let's call it area cell. Is an XR open dataset file path 2. And we're going to merge these two files into one dataset. So, for our convenience, we only keep track of one dataset. So DS merge data and area cell 0. Or, well, I should be consistent with their notebook. They call it cell O. Okay, and then let's output this DS and let's just take a quick look at it. Okay, so it took a minute because it needed to download the files. Okay, so you see here, we merged the two files together to create this single data set, and the dimensions are time, D2, I'm not sure what that is, but it's probably not important for our purposes, latitude, longitude, and levels. So it's a global data set, and it covers the time period of, well, we'd have to look at that. Yes. From 2000 to, okay, I don't want to scroll all the way. 2000 to 2014. And we have data variables of time bounds. It's not really relevant for us. The most relevant variable is TOS, which represents the SST, sea surface temperature. And what other information do we need? So it's on a 1x1 grid. So this data set has a resolution of 1 degrees because it's on a 1x1 grid. And then another variable we're going to use later is the area, T area variable, because eventually we'll want to weight the SST by area. Okay, hopefully you all are still following along and coding alongside with me. Okay, so now we're going to plot SST on the first timestamp using Cartopy. And I believe you guys should have already been exposed to Cartopy, but this is where we get to apply it to real data, real science. Okay, so we're going to first create a figure object. So equals plt dot figure. And we're going to set the figure size to 12.6. And then we're going to set the axis to have a projection of Robinson. So I wonder if this DS tells us which projection it prefers. In the attributes, the geospatial data sets usually tell you the projection you can use for their data. I'm not seeing it, but I'm also not looking very closely, so maybe you guys can look closely if you want to, but I will move on for time purposes. So plt.axis, and then we're going to set the projection to CCRS, Cartopy, Robinson. And central longitude equals 180. This information is usually provided in the attributes of the dataset, but I didn't see it. But like I said, I wasn't looking closely. And so now we're going to add, just to make this figure pretty, or actually, let's see what it looks like without doing that first. So let's jump down to the last line and plot this variable, SST variable. Selecting the first time slice, we're going to plot it, AX equals AX, just so that we're lining it up with the axes. And then the transform will be CCRS plot Xarray. I don't know how to pronounce that. Plot Xarray. In my own experience, I've never used any other option besides plot Xarray, so it's very common. We're going to set the minimum temperature value to be -2. To visualize, we're going to set -2, and then the maximum 30 degrees. The units is Celsius. Let's see if we can see that. Yep, degrees Celsius units. And it is usually units, ocean data. I mean, Celsius temperature data. Okay, and then we're going to set the color map, so CMap to cool. I just started a new line within the parentheses so that I won't have to deal with the scrolling over. So it's easier to see the code. CMap equals cool warm. Okay. And let's plot that. Might be a little slow. In my experience, plotting with Cartopy usually is slower than plotting with Matplotlib. I imagine it's because it's just more complicated operations happening under the hood. But it shouldn't take this long. Has anyone else plotted it yet? And remember, I can't see the chat, so you'll have to unmute yourself. Huh. Well, it doesn't even show that it's running. But there we go. So this is the first time step of the sea surface temperature, global sea surface temperature, projected onto a Robinson projection with Cartopy. And so now we can clean it up a bit by adding some coastlines to make it seem more realistic. So AX dot coastlines. And let's see, we can also add grid lines to help ourselves. You know, if we want to focus on a specific region, spatially, we can use the grid lines to help. So AX dot grid lines. Cool. Looks legit, doesn't it? Okay, moving on. So it's great. We have this global data, but our focus is the El Nino region, which is the Pacific region right here. So we need to create a box essentially. So we're going to slice the data to the El Nino region, such as this one here. So down below, we're going to create an object variable with the slice box region of the Nino 3.4 region. You can either use the cell method or the ICEL method. For in my experience, a lot of times I use the ICEL method, but the cell method is very useful when you want to keep track of your labels. Okay, so we're going to call it TOS Nino 3.4 for the 3.4 index. And then we're going to select it by slicing latitude from -5 to 5 and longitude from 190 to 240. And let's look at it. Okay. So still kept the time dimension, of course, but now you see latitude and longitude are have smaller index values because we sliced it. And now, oh, so that's one way to do it. And here they're showing there's a different way, like what Kevway showed you, using the where method. So we're just going to call it the same thing because this is the method we're going to stick with. So ds.cell, or sorry, no. ds dot where. And we're going to say, for the latitude, we're going to say, this should be in parentheses, ds dot lat 5. And so we're going to keep the values that are less, latitude values that are less than 5. And ds dot lat that is greater than -5. And hopefully that makes sense why we're doing it this way, because here we were slicing from -5 to 5. So we want the values in between -5, so -4, -3. And down here we're saying, okay, our upper limit is going to be 5 degrees and our lower limit is going to be -5. So don't keep the values outside of those bounds that we are setting for latitude. And same logic for slicing for longitude. So ds.lon less than 240. And then sorry. ds.lon greater than 190. And let's just move this to the next window so we can see better. And then we're going to just drop the rest. Drop the rest of the values because we won't need them. Let's see. Okay, so they should have the same shape, and they do, as you see here. Another way to check if these two methods have the same shape is to do dot shape. So we should call this so. And then so you can say TOS Nino dot shape. Oh, you need to select the variable, not the data set. You can do the shape method on a data array, but not a data set. So TOS. So that is the shape of this data set here. And the previous data set where we use the method of cell has the same shape. So that's another way to confirm that both methods give you the same output or same result. And so now let's plot it. Let's plot the SST of that region. So we're just going to use the same syntax as up here, the Cartopy way. Please let me know if I'm going too slow. Maybe I should check the chat just in case I missed anything. Where's the chat? Okay. Okay, so I'm just going to assume that this pace is good for everyone. Okay, so now we're going to plot it like I said. So let's create the figure object. Figure, same size, big size equals AX equals P. See, nice. Since equals Robinson equals 180. And if I don't know if anyone taught you guys some shorthand ways to code, but if there are long arguments that you don't want to type all the way out, you could just type up some of it and press tab, and Python will just autocomplete that for you. So that'll just save you some time if you don't want to type out everything, but it also helps avoid any typo mistakes. I think I showed these shortcuts the first day of the online school, but I think it's worth repeating because it helps just with the flow of your work as you're coding. So B to add on your keyboard, you could press B to add a cell below, or you can press A to add a cell above. instead of having to always click on this plus button here. And then to run the cells, Shift Enter is the quickest way rather than going up here and pressing this button all the time. Anyways, I just really love shortcuts because they make my life easier. So hopefully they can make your lives easier. Coastlines, next dot grid lines, and then we're going to plot the actual thing. So TOS, we're using this one. .TOS, we're selecting the first time step. You can select a different time step. 0 is just easy to start with. And then we're going to plot. Same syntax as before. So transform. I could have copied and pasted, but as I keep saying, and I really do believe that practice is really good. So it's just good to type it all out and just practice it, you know, because that's when it stops being intimidating and starts being useful for you. So vmin equals -2, max equals 30. We're going to use the same color map. CMap equals cool warm. And then now we're going to set the extent. Set the extent of the region. So I did Shift Tab to see the like the short documentation on this method, and this doc string says set the extent with your longitude values and your latitude values of your map in the given coordinate system. Because even though we sliced up this data set in Cartopy, I believe with since you are projecting like this plotting method, you are projecting, you need to set like real spatial latitude and longitude values because it's going off of reality. I don't know. That was a poor way of explaining it. 310 -10. Okay. There we go. So that's the box with the sea surface temperature at the first time step in the Nino 3.4 region. And you can just visually check with this figure up here. And, you know, with Australia to the left, Central America to the upper right corner, it looks like we're getting closer. So now, as I said before, the Nino index, the Nino 3.4 index, it doesn't represent the sea surface temperature. It represents the anomalous sea surface temperature. So now we have to compute the anomaly, but we have to compute the rolling mean of the anomaly. Okay. So the first thing we're going to do, so there are 3 steps. First, we do the group by method. Then we're going to subtract the mean SST from the climatology or the monthly data. And then we're going to get the anomalies by computing a weighted average. That's why we needed that second file of the area, the grid cell areas. Okay, so let's first do the group by. So group by GB object equals our sliced SST region, our SST variable group by, and then we're going to say we're going to group by month. So it's going to be in the time dimension, we're going to focus on the month. And so I'm not sure if someone told you what group by does. Maybe Kevway did, but maybe I wasn't present at the time. But just to reiterate, if you have already been exposed to this, group by, what it does essentially is if you specify month, like you want to pull the month, what it's doing is that throughout the, 14 years, because it's from 2000 to 2014 of the data set, through the 14 years, we're going to take all the Januaries and put them in one category. We're going to take all the Februarys, put them in one category, and so on. And so what you have essentially is, instead of 14 years, you're reducing the time dimension to only be 12 months. And so that's what this step is doing. And now we're going to subtract that from the mean, from the time mean of the data set, in order to get the climatology. Or no, sorry, in order to get the anomaly. So we're going to call this TOS Nino 34 anom for anomaly. And we're going to subtract it from the monthly mean. Dim equals time. Another way to do this, here, I'll just show you, because I don't know, people learn in different ways. So it's just helpful to show different ways to do things. So you could say the climatology, where it's essentially this, but instead of having the mean be integrated in the anomaly calculation in this line, you could put it here. That way, it finishes this operation of creating the climatology, where, like I said, you're grouping all the months together. So you have January's, you have February's, and from that, the operation we're doing is we're taking the average. So out of the 14 January's in the data set, we're going to find the average of that. And then we're from the 14 February's that we have, we're going to find the average of that. And then from there, you would say anom or TOS Nino 34 anom equals this minus the climatology. So that's just another syntax way of doing it, if that makes more sense to you. But I'm just going to go ahead and do it the way the Pythia people wrote it. Okay. And now we're going to weight it. Index. This is where it starts becoming the index, because we're going to weight it by area. 34. Nom dot weighted. Oh, weighted. TOS. Okay, TOS. There we go. TOS for area. So dot mean, and let me just expand. Oh yeah, lat lon. Okay. Mean. Okay. Let's just look at it. Cool. So now it's a time series. Now the only dimension we have is time, because we took, we weighted it by each grid cell, and then we took the spatial average over lat and lon. So now our only dimension we have is the time dimension. Okay. Let me take a break here just in case people need to ask questions, or just to catch up with the coding. Okay, so part of the definition of the Nino index, the 3.4 index, is that it's a 5. In order to categorize an event as an El Nino or a La Nina event, they look at how how do I explain this? We take the 5-month average. Here, 3.4 index typically uses a 5-month running mean for the events in order to define them as La Nina or El Nino. So now we have to do a rolling mean or take a mean over a rolling window using the rolling method. So let's create that index. I'm gonna call it rolling mean. So from our index object, we're going to say rolling. And here is the quick doc string on this rolling window object for data arrays. And this is the input that it expects, the dimension over which we should do the rolling. And the only dimension we have left is time. So rolling time equals 5. And we say 5 because it's monthly. It's monthly data. If it were daily, then that would be different. It would be like 365 times 5. Okay, so over 5 months, we're going to make our window center be centered. So we're going to say true, because you can have your rolling window start in the beginning, the center, or the end, I believe. So we're going to say center equals true. Mean. Sorry, this should be outside. Mean. And I believe that's it. Yep, that's it. Sorry, I'm expanding my other window. Just making sure I don't make any typos. So we created that, and now we're going to plot it. So, we're going to plot it. So we're going to plot this rolling mean against the original, against the index. Index. Starting with that. So these are going to be line plots because they're a time series. Dot plot. We're going to create a legend so that we can tell which line belongs to which data. So since we're plotting this one first, we're going to say it's the anomaly. And then the second one represents the 5-month running mean anomaly. And then give a title, PLT, title, SysT, anomaly over the Nino for cool. So the orange represents the smooth data, and visually you can see that because the blue line, the anomaly that wasn't smooth, is more jagged. The peaks are more pointed. Okay, so since the ENSO index conveys the deviations from a norm, the calculation of Nino data requires a standard deviation. So now we have to compute the standard deviation, but it's simple. It's just one line of code. So TOS Nino 34, and it's this method called SCD for standard deviation. Reduce this data array's data by applying standard deviation along some dimension. And since there's only one dimension, we don't need to specify. Cool. So that's the standard deviation. And now the final step of the index calculation involves normalizing the data. And I just wrote a note here. We usually want to normalize the data so that it makes the data unitless, because an index is a unitless measure. And it changes the values of our data to become a common scale, so it's easier to compare with other types of data that may have different units. So now we're going to create object variable where it's normalized. So normalized index. These variable names are becoming very long. Really mean. From the index, really mean divided by the standard deviation. And that's that. Easy. Okay, so now we're going to visualize the normalized data. Okie dokie. So fig equals plt figure is the same syntax as before, creating a figure object, fig size equals 12. So now I'm going to type this out and then I'll explain after what each line is doing. So we're going to we're going to highlight the El Nino events. That's what we're doing. So normalize index. Normalize it. So this is where the tab completion comes in handy because we have really long variable names. So just pressing tab helps finish it for you and avoids user error of any typos that may occur with long names or titles. Normalized only mean. .4 Celsius. Dot data. Okay. It's going to be hard to keep track of it. Let me just clean this up a little. Okay. And then 0.4. Color should be red to represent anomalously warm events for El Nino. And the alpha sets the, what do you call it? The opaqueness of the filling of the color. One would be totally red, but if you were to put like 0.2, it would be like a very sheer red, like you could see through it, but we're going to set it as 9. And you could play around with this after setting the alpha to be different float values. And now we're going to do the same thing for La Nina. So instead, we're going to change this to be less than negative 0.4. And these values, so the reason why it's 0.4 and negative 0.4 for highlighting El Nino and La Nina events is because in the definition, 0.5 values above 0.5 degrees corresponds to El Nino events, and values below negative 0.4 corresponds to La Nina events. And these are denoting like separations of where those events will occur. Okay, and instead it's going to be blue for anomalously cold. And then we're going to plot the normalized data. And it's going to be a line because it's just a time series. So we're just going to set the color of the line to be black. And we're going to add horizontal lines for both El Nino and La Nina events. And in the center, 0. Color equals black, or we could just say color equals K for black. And then LW line width equals 0.5, or you could actually write it out saying line width, but LW is easier. PLT dot next inch line. So for El Nino, 0.4 color will also be black, but same width, but the line style will be dotted. Same thing for La Nina, but except it's negative. Negative 0.4. Okay, and then lastly, we want to create a title of what we're plotting. What are we plotting? We are plotting the El Nino for index. That doesn't seem right. So this is supposed to look like the figure up here. Let me just, oh, another short keyboard shorthand is if you want to copy and paste, to copy, you press C. And then I just want to paste it below so it's easy for us to compare. And then in order to paste, you press the letter V on your keyboard. And then I'm going to take all of these away so that we can just easily see the figure. Oh no. Oh, okay. So that's what it's supposed to look like. And so now I'm trying to figure out what I am not doing correctly. So we have the horizontal lines here, right? They put their horizontal lines to be -1 and 1. But that doesn't matter. Let's see. If you guys have any suggestions, please let me know, but just give me a moment, please, to just compare the code with Pythia's notebook, make sure I'm doing everything correctly. Might be here. Oh, sorry. Right. Yeah, that should be fine. Hmm. Yeah, I'm not sure what I did incorrectly because I was just going off of the notebook, but hoping you guys get the idea where the red represents El Nino events and the blue represents La Nina events. And I guess while I still try to figure this out, please unmute yourself or I can open the chat now. And please ask any questions or if you can offer any suggestions on what I could do to fix it. This is the original notebook, so I'm going to run this in its entirety and see. Just to make sure the output should look the same as the figure. Right, it should look like that. So I'm going to copy and paste this into the other notebook. Aha, so is something wrong with this cell? Okay. I don't see what I did differently because I just quickly went through it line by line. But this is, so let me just delete this cell. This is what it should look like. Not quite the same as this figure, but that's because this figure is going from 1950 to 2020. So if you wanted to really compare apples to apples, so to speak, you would have to look at it over the same x-axis or the same time frame. But I guess you can kind of interpolate with 2000 to 2014. So 2000 to 2014. We have 1, 2, 3, 4 peaks. 1, 2, 3. Oh, but this is 2015. So 3 peaks and 3 peaks. Yeah. Okay, so that is the ENSO lesson. I will stop recording or pause recording, actually.